Excuse me. Good afternoon. My clock says it's straight up 12 noon. We'd like to welcome everybody here to the Dairy Building Design in a Changing Climate webinar. This is sponsored through the I-29 University Group, which is a collaboration of dairy specialists from the South Dakota, North Dakota, Minnesota, Iowa, and Nebraska. Today's webinar has Dr. Akdeniz, who's an assistant professor and extension specialist in biological systems engineering at the University of Wisconsin-Madison. And she will discuss how increasing temperatures and extreme weather events affect the design and ventilation of dairy buildings. She will also cover ventilation techniques that enhance airflow rates and considerations for energy efficiency and reducing ventilation-related greenhouse gas emissions. I would also ask that also has the link where we will have this archived. And it usually takes us about 5 days before we get the program into the archive. At this point, I'm going to turn it over to our speaker. As I always say, Dr. Nesli, the podium is yours.
Thank you very much, Fred. Yep, good afternoon, everyone. I'm Nesli Akdeniz. I'm an assistant professor and extension specialist in biological systems engineering at UW-Madison. So today I will talk about dairy building design, mostly ventilation design. My focus will be on ventilation design in a changing climate. All right. Sorry about that, my slide got stuck. So we tested this one before we started it work, but now it doesn't work. So let me share my screen one more time. I apologize for that. All right, okay, now it works. I apologize for the pause. So I'm not a climatologist, so I don't want to dive into climate data, but I want to show you a couple of slides so that we understand what kind of changes that have been happened over the last 30 years and what are the predictions for the coming years. So I think the easiest thing to measure is the average temperature. So we have a lot of data related to temperature increase. So just above the surface they measure. So average temperature in the United States has increased about 1 degree C. So they say 0.7 to 1 degree C. And the most substantial warming has occurred in the last 20 years. So when we look at the Midwest data, so I'm located in Wisconsin, right? Wisconsin, Minnesota, Illinois, Nebraska, Iowa, and South Dakota. So the Midwest increase is similar to the national average. So it is a little bit maybe above the national average, but about 1.3 degree F to 1.7 degree F. And the one thing that is very significant is that precipitation change. So this region has experienced more rainfall, and more rainfall means higher humidity and warmer nights. So, and then we will talk about why warmer nights matter. So in this slide, we are looking at the average temperature trends. So for the last 30 years, and then maximum temperature trends and the minimum temperature trends. So average temperature trends, so there is a more increase in temperature in western states. So when we look at Illinois, Iowa, Minnesota, Nebraska, and South Dakota, so we see a little bit increase, just like I mentioned, maybe around 1 degree C. Maximum temperature trends, maybe these temperature trends, they are responsible for those high daytime temperatures and heat stress the cows experience. And the minimum temperature trends, there's a little bit increase in minimum temperature trends over the last 30 years. And this is important since, as you know, like daytime temperatures can be high, right? But if it cools down during the nighttime, then cows can take a break and then they can recover from the heat stress they're experiencing. Maybe if it is only 1 day or 2 days, they may be able to recover. But if it continues for a couple of days in a row, if daytime temperatures are high, nighttime temperatures are high, then it makes it difficult to recover from that situation, the heat stress animals experience. And they cannot, there are animals, they cannot go back and they cannot grow up and continue the produce. All right, so Father's Day weekend is coming. So this is the heat index forecast for this weekend for the next 6 days. So when we think about heat stress, it is not just the temperature, it is temperature plus humidity, right? We are talking about temperature humidity index, THI values for cows. So if it is between 68 to 71, we say mild heat stress. Probably like if we look at the Sunday data, so if we look at some part of Iowa and some part of Nebraska, they will be in that extreme caution zone. So probably cows will experience moderate, may experience, if there are no mitigation techniques in charge, right, from moderate to severe heat stress during those days. So it is difficult to predict. So this is just the forecast, but this is what is waiting for us in the following 6 days. All right, so temperature is a little bit easier. So there are a lot of predictions related to temperature, how much it increased, what the expectations are for the following years. But when we think about the wind speed and wind direction, they are important when we think about natural ventilation. Even they are important for mechanically ventilated buildings. So if temperature will change, so this is what they are expecting, forecasting. So if temperature will change, those changes in temperature, right, temperature gradients, and there are a lot of changes, right? Things have changed. The land use changes. They play a role in wind patterns. So IPCC predicts a 10% decrease in wind speeds by the end of the century. So there are a lot of discussions. Most of these discussions are related to energy generation, wind turbines. So if we are going to have a wind drought, how it will affect energy generation. So there are a lot of studies and a lot of discussions. Some studies suggest that wind speeds will increase in the Midwest region, so we will be advantageous in terms of energy generation. So some scientists say like that. But we can look at a couple of data points, so a couple of graphs. So in this slide, we see the average wind speed. So in last year, so this year's June data is not ready. So I collected data from last year. So we are looking at June 2023 and July 2023. So when we look at the blue parts, they show the slower wind speed. So this is data relative to the recent 30 years. And those pink or red, oranges points, they mean that faster wind speed. So if you look at Midwest region, if you look at Wisconsin or Iowa, Minnesota region, we see for June, we see the wind speed, average wind speed. So this is 10 meters above the surface, is blue. So it is slower, so less wind. So when we look at the wind U component, so it is here, wind U component. So they call this one, U component is the wind from west to east. So in the Midwest, wind blows from west to east. In winter, it is much more like northwest to west. And in summer, it is southwest and west. So west to east, there's a decrease. And when we look at the V component, so this is much more like north to south way, there is a decrease in that one too. But this is just one graph, one data point. There's so much data there and so many years, so many months. But if you look at the July average, so again, there's a decrease in the mean wind speed. West to east, there is an increase. So there are some discussions. So our building design is, we design our buildings assuming that wind will blow from west to east, right? We will take advantage of that one. But if there will be a shift, if it will not blow from west to east, or if there will be a little bit shift, if it starts blowing from north to south, then it will affect all our ventilation design, especially for naturally ventilated buildings. So when we look at the west to east, there's an increase. And when we look at the north to south, there's a little bit decrease. So what I am understanding is difficult to make like solid conclusions related to weather data. But what I am understanding is we may experience a little bit decrease in wind speed, but in the following years, hopefully wind will continue to flow from west to east, not in near future, but in the long term, they are expecting that there will be a shift in wind direction too. But for now, it is mostly from west to east, as we always experience. All right, so there's a pointer. So precipitation data. So I purposely put these two graphs here. So this one shows May 2023. This is May 2024. So it is very difficult to predict weather patterns, right? It changes a lot. So I'm located in Wisconsin. So last year in May, in June, we have very severe drought. My grass outside was completely yellow. This year we had storms, we had flooding events, and then it is like we got more precipitation than the average value. So we never know, and it does make it difficult to design a dairy building, right? So if we know it will happen, we don't hesitate to invest in a mitigation technique. But if we don't know if it will happen for sure, then should we invest? Should we make that investment? Is it worth spending our money to mitigate something that may never happen, right? It is the challenge. So I think having some backup plans, having plan B is kind of the way we are moving forward in the following years. So this is my last slide related to climate. So I did a lot of pasture studies. I tried to do actually pasture studies last year. So we want all our cows to be outside under, walk around under fresh air and just enjoy the sunshine. But there are reasons, right? We cannot put most of our animals are outside. So one reason is the climate, right? It sometimes helps to have a roof on top of the animals. And then like if you look at the data here, so I'm showing data for Wisconsin, but we can see a little bit for Iowa too. Due to drought, all pastures shut down early last year. So all our studies, like we collected data halfway by August, all pastures shut down. So this is here, I am showing livestock forage disaster program, eligible county payment months in 2023. Most of the counties, not all of them, but most of the counties were eligible for 3, 4, or 5 months of payment. So this is one of the reasons we put all our animals indoors, not all of them, but maybe 90% of our dairies indoors in Wisconsin. All right, so these are the animals indoors. So I will start with natural ventilated buildings. I will show you a couple of examples. Then I will move forward with the mechanically ventilated buildings and some modern buildings and the relationship between the ventilation, energy consumption, and GHG emissions. So this is a building located in northern Illinois. So this is a fabric barn. So it's made of fabric. As you can see, it still has that steel frame. So you can see the steel frames, but the barn itself is made of fabric. And this barn is out there for more than 10 years, and the farmer is very happy with this building. It's very bright since it's made of fabric. There is that natural light. And one thing that you can notice is there are no ventilation fans. So there are a couple of circulation fans that circulate the air inside, but there are no ventilation fans that bring fresh air from outside. So this is a natural ventilated building and it works very nicely. So it's housing 180 cows. It has that east-west oriented. So it is, this part is heading to west. Sorry, this part is heading to east, and the other garage door, we cannot see the other side, is heading to west. So one thing that we notice when we enter this building is it's very quiet. So it is almost a place, you know, air quality is exceptional, it's very quiet. It's almost a place you can sit down and read your book. It's so bright and so, you know, airy inside. And there are a couple of reasons this barn works this way. So reason number one, so it is on top of a hill and there are no buildings around. So there are no parallel buildings. Maybe I needed to take my drone and take a bird view picture. But I think this picture tells us that like wherever you look, there are no buildings. So it has that east-west orientation. So it is capturing all the wind, the prevailing wind, all the wind that is coming from west. So it has almost, it has, natural ventilation and natural ventilation fans almost, it works like that. So when there are, adjacent buildings, they cause downwind effects up to 10 times of their height. So if there are many buildings around, they block the airflow rate, and sometimes natural ventilation doesn't work anymore. But this was not the case in this building. Another reason we can see that it has a very steep roof pitch, so it is 6/12. So lower pitch, it means slower air movement. So it traps warm, moist air against the cold roof. So air is having harder time to exit from ridge vents. So higher steep, like the higher the building, the natural ventilation works better since it has that chimney effect. So maybe it is a little bit more expensive to have steeper pitch, but it increases airflow rate. One concern with steeper pitch may be in cold weather, then the air distribution may not work very well since animals don't generate that much heat in winter, and the air movement might be difficult. But in summer, since a lot of heat is generated by cows, and as you know, hot air goes up, so has that chimney effect. It works very well in summer or in warmer climates. And then ridge design. So it has a proper ridge design. So this is another reason this barn is working. So we are expecting 1 to 1.5 inch per 10 feet of barn width. And then some bridges are covered. In this example, it is not, so we can see it is all the way. So, but the holes are small enough so it doesn't cause a lot of rain and snow to enter. There is some humidity problem for sure. We cannot say there isn't, but it is not a major problem. They're small enough. And then what the farmer said, in winter, those ridges are blocked by ice, and even it doesn't let any rain or snow to come inside. So in winter it works, and in summer it also works. So one thing that we need to pay attention, maybe they need to be 8 to 12 feet from each barn end to minimize downdrafts. So you can see it stops here, so there's a little bit distance. So also this farmer has some automated milking robots. So if you have those kind of robots, then you have that space to put your robots. So there is no rain dripping on top of your robots or snow or moisture coming. So it protects your robots from the weather situations. All right, so another reason they have the adjustable side wall inlets. So these are split curtains, so they just close the bottom during winter and keep the top part open, partially open. And then in summer, when it gets very hot, so they open it all the way. So you can see, maybe it's a little bit difficult to see, but I can point you out. So this is one, and this is the other split curtain they have. So, and then they can just close it if it is getting colder. So I think the side wall height was 13 feet. So the recommended side fold is 12 to 16 feet. So it was within the range. And as you can see, there are a couple of circulation fans. And I believe this farmer brings in some box fans. So when during regular weather situation, climate, this barn natural ventilation, it works. But we start to experience more weather extremes when it gets very hot, and then wind doesn't blow. When we reach those days, maybe they are just a couple of days in 1 year, not maybe more than 10 days, but there are those kind of extreme weather days, right? And this farmer is very well prepared for those extreme weather situations. So he has circulation fans, and he also has sprinkles, though, so they help during the extremely hot and no wind conditions. Since this is natural ventilation, if there is no wind, if there is no air moving through, then it's difficult to ventilate these buildings. So there are a lot of studies and discussions about like sprinkles and mister systems. So this farmer has the feed bunk sprinkles. So they are also called soakers. So the important thing here is to keep the feed dry. So feed is dry, but the water penetrates the cow's skin. So it has that evaporative cooling effect. So Mr. Systems, some people recommend Mr. Systems less consumption when you have a Mr. System compared to the sprinkles. But Mr. System, if there is wind or if there are ventilation fans, so they will not penetrate the cow's skin. They maybe just carry it away with the wind, and those droplets may never reach to the cows. But the sprinkles penetrate the cow's skin, but they may increase the relative humidity of the barn. So if it is hot and if we are increasing the relative humidity, it doesn't work well, right? So it just increases the risk of having heat stress. All right, so one concern, since this barn is on top of the hill, and when there are fewer buildings, there tend to be more birds around. So if you have only one building and this is a beautiful, natural light building, all birds want to go inside. So bird screens may help. This is one of the things we were talking with Fred before starting this webinar. So bird screens may help. So by the side curtains, side walls, having those bird screens. So we not need to open garage doors. So we cannot avoid birds to go inside completely. But considering these avian influenza outbreak concerns, so it may help to reduce the number of birds we have inside the buildings. This was one of the concerns when I visited this farm. And it doesn't need to be a fabric natural ventilated building. There are so many natural ventilated buildings, especially in Wisconsin, family-owned natural ventilated buildings. Most of the buildings are naturally ventilated, and they worked very well, no problem with them. I think the only concern is those extreme weather situations, that when we have that heat wave, if there is no sprinkle system or if there is no additional fans that will help to move the air through the barn, then those days might be problematic. So usually the minimum standard is 1 feet of sidewall opening on each wall per 10 feet of building width. So this is the standard, but it may change depending on the needs of the building. All right, so if natural ventilation doesn't work, then the plan B, the alternative way, is to have tunnel ventilated buildings. So in tunnel ventilated buildings, air moves perpendicular to animals, to stalls, and ventilation fans are placed on the end wall, on that short wall at the end. So here we see the ventilation fans. And then if there isn't enough space, usually there isn't enough space on the end wall. So some of the fans can be placed on the side wall. So we want the air to move, from coming from one end wall, one side, and then to leave the other side. So we don't want to have these side wall fans. But according to our studies, if there aren't many, if most of the fans are on the end wall and just a couple of them, the ones that do not fit on the end wall, if they are put on the side wall, and that is okay, it still works. So let's look at some simulations. So these are computational simulations, computational fluid dynamics simulations. So we are seeing the tunnel ventilated buildings. So these are our air inlets. And this is the way air flows perpendicular to stalls or animals. And here you can see those small circles are our ventilation fans. So they are drawing the air through the barn all the way. So it's a little bit difficult to see, but we can see here some of them. We cannot see all of them. There are a lot of circulation fans. So these small circles are our circulation fans. We can also see this way. So I'm pointing them out. And then this barn, so again, these are the circulation fans. This is our air inlet, and this is the way air moves. So this barn, it also has ridge vents. So ridge vents in a naturally ventilated barn, it serves like an air exhaust, right? Air outlet. But in this example, in this barn, since we have the exhaust fans, ventilation fans here, these ridge vents, they serve as an air inlet. So I will show that one to you in a second. So, okay, this is how it looks like. So these are the ventilation fans, right? These are on the short wall, and this is the one that doesn't fit, so it is on the side wall. And here we are looking inside the barn. So these are those small circulation fans. As you can see, many of them. Since these barns, they have the tunnel effect, right? Air comes in and it leaves. But if we don't have the circulation fans, only the feed alley will be ventilated. We need to make sure that animal occupied zone where the animals are ventilated and circulation fans, they do that job. And here we can see the ridge ones, so many of them here. So the advantage of this barn, I really like the design of this barn. So this was a naturally ventilated building, original design. So as you can see, it doesn't have a very steep roof. Probably natural ventilation didn't work very well. So it's not a brand new building. Maybe it is out there for 20, 30 years. So that what the owner of the barn did, he installed those tunnel ventilation fans, and now it works very well. So it is again natural ventilation in winter. So you can see the curtains. We already have the ridge vents, right? And it is tunnel ventilation in summer. He just turns on his ventilation fans, exhaust fans, and he has that additional air exchange rate that he needs in summer. So yeah, it's a very, very clever design actually. Okay, so we are looking at the computer simulations. So here we are looking at the temperature. So on a nice sunny day in Wisconsin, we assume outside temperature is around 27, 28 degrees C. So this is the air coming inside the building. As you can see, air tends to move like through the middle alley, feed alley, since there is no obstacle on that way. But this is where the animals are located. So this is where our stalls are. These are the areas, right? We have the stalls. So where the animals are located, so it is a little bit warmer, right? It is since the animals are generating all that heat. But if we don't see a very huge temperature increase, if temperature increases within the region like 2, 3 degrees C, if it doesn't, exceed 5 degrees C, then we say it's a successful design, it works. So here we are looking at the velocity data. Okay, so here again are air inlets, and these are our exhaust fans. So air in the air inlet, air velocity is the highest, so air flows through the barn. And then we have reduced velocity where the animals are, where the stalls are. And this is why we need all those circulation fans. So they are usually tilted 45 degrees and they're blowing towards the animals so that it does help with the air circulation. All right, so one concern of this one when we visited was having those rich vents in summer. So they were open, they were not plugged. I understand in winter they help with the natural ventilation. Air comes from side curtains and it leaves through the rich vents. But how does it work in summer when ventilation fans are on? So my concern, so here is the barn. Okay, we are looking, so you can see this gray area, right? We are looking that kind of cross-sectional area here. So we are looking at the velocity. So these small circles are my ventilation fans, exhaust fans. This is my air inlet. Okay, and this dark place is difficult to see is where my animals, stalls and the cows are. And these are the rich vents. So my concern was the first one or two rich vents will serve as main air inlet and no fresh air will go through this part of the barn. But as you can see, it's a successful design so that this air inlet, so here is our air inlet, right? Our main air inlet, let's call it main air inlet, it still serves as the main air inlet. So most of the fresh air comes through our main inlet. And these rich ones, they just help. So they just provide a little bit fresh air. So there is no shortcut here. So it doesn't cause having these rich ones, it doesn't cause having a shortcut, but it does work if we are able to pull fresh air through the barn all the way. All right, so we talked about natural ventilation, tunnel ventilation. So if tunnel ventilation doesn't work, then plan C is cross-ventilated buildings. So here we can see it's difficult to show cross-ventilated building. Usually tunnel ventilated buildings, they have that, rectangle shape, but cross-ventilated buildings, they are much more like a square. So a little bit difficult to see, but what we are seeing here is most of the cross-ventilated buildings, they don't have the circulation fans, but instead they have the baffles, right? And then this is kind of where the air inlet is. This is not a good picture, but I can see the light is coming from here. So it is the air inlet. And the other side of the barn, so this is where the exhaust fans are located. So let's look at the simulation. Maybe it is a little bit easier to explain. Again, we are looking at the temperature data. Okay, so this is our air inlet. So in this barn, it is heading to south. So, and this is small fan circles. This is where our exhaust fans are. And this is our middle alley. And then these are our stalls and these rectangles. So 1, 2, 3, and 4. 4 of them, those are the baffles that are, pushing the air down. So we are looking at the velocity here. So again, air inlet, our exhaust fans, and our baffles are here. So when we look at the temperature data, so again, our outside temperature is around 28 degrees C. This is our assumption. So the first rows are very lucky, right? They get all the fresh air. So air warms up as it moves towards to the exhaust fans, since the air picks up all the heat generated by the cows, right? But if the temperature increases, so I can see temperature is increasing from 28 to 30, maybe 30.5. So if temperature increase is not very significant, then we call it a successful design. As you can see, the air moves this way, so we can see the air flow patterns here. And then we will look at the baffles in a second. Okay, here's the baffle slide. So I really like baffles. So in my opinion, I say it in many different places, but baffles are a genius idea. They don't consume any electricity, no energy consumption there, but they work very well. So let's look at the simulation. So this is our velocity. So this is our air inlet. This is our air exhaust, so air moves this way. So it comes and hits to the first baffle. So, and the color changes from dark blue to light blue. So the air velocity increases. And it hits to the second baffle, and that it's whenever it hits to the baffle, this is very like visible here, it pushes air down where the calves are located. So we don't care about ventilating the upper space inside the building, right? We want to ventilate where the calves are. So especially when calves are sitting, heat accumulates under their legs. And so we want to ventilate calves sitting height. We want to ventilate calves standing height. So baffles work very well in that sense. So it pushes the air towards the calves. So having baffles, so they are not aesthetic looking. They don't have an aesthetic looking. It's kind of like we don't like baffles. They don't have that beautiful looking, but in terms of airflow rate, increasing airflow rate and improving the ventilation, they help significantly. But one thing that we need to keep in mind is each baffle, whatever we put inside the barn, so it can be stalls, cows, even human, robots, everything, and baffles, especially baffles, they add to static pressure. So static pressure, we can think about static pressure is kind of like this, the resistance to flow. We can think like that. So if we have high static pressure, then our exhaust fans will have a difficult time to pull the air through the barn, right? So if we add new elements, new components to the barn, if we add new baffles to the barn, it will increase the static pressure. So yeah, one thing that we can think about is we need to keep in mind when we are purchasing ventilation fans is there's something called ventilation efficiency ratio. So the unit is CFM per watt. So how much CFM, how much air I will move per watt energy I consume, right? We want the efficiency to be high. And there are different brands, different sizes. So Best Lab in Illinois is a certified lab. If you visit their website, so you can get that information. So it's just like purchasing a car, right? We think about fuel efficiency when we are purchasing a car, but it's not the only thing we worried about, right? So when we are purchasing a ventilation fan, the situation is similar. So we are worried about the fan efficiency, but it's not the only thing we worried about. So here's a table you can find if you visit Best Lab website. So here we see the static pressure. So once we, let's say at 0.1 static pressure, fan efficiency is 19.3 CFM per watt. So if we increase 0.15, then the efficiency will go down. So static pressure increases and efficiency goes down. So we need to keep that one in mind. All right, so we talked about natural ventilation, tunnel ventilation, cross ventilation, and I want to talk about a couple of slides I prepared related to modern buildings. And what I am referring by saying modern buildings is buildings with AMS, automated metering systems. How is it related to ventilation design? How is it related to climate change? So I will explain it in a minute. But what we are seeing is there are increasing number, right? Automated milking systems are being increasingly adopted. So like in 2000, there were only 800 AMS units in the world, not in the United States, but in the world. Now they're expecting the number to be over 35,000. And they are projecting that it's a very like growing market. They are projecting it to reach the 4.3 billion by 2027 in a couple of years. So there are some financial concerns, but there are some advantages, disadvantages of AMS units. I think one advantage is it reduces labor requirements, so it helps with the work-life balance. So I can see that. So the number will increase. We will have more and more AMS buildings. So once we have these AMS buildings, then the building design changes, right? So once we have put these AMS units inside the building, so there are different types of designs. So one is free flow, one is guided flow. Especially in guided flow, so there is something called, there is that commitment area, commitment pen, right? Animals enter that pen and they wait their turn to be milked and to eat those pellets, right? And then they go to the feed alley and eat. So while they are waiting here, so we can see a little bit, while they are waiting to enter the robot, this is called kind of like heavy traffic area. Okay, so these AMS units, they are like square shape. So we put them in the barn, right? They block the airflow rate. And there is this heavy traffic commitment area. So that area also blocks the airflow rate. As you can see, most of the time, like I can show you here, there are very big circulation fans. They are tilted. I believe they are 45 degrees. So they are circulating that low airflow rate area. Okay, so without having those circulation fans or without having a mitigation technique, then that area is kind of susceptible to heat stress, so having high temperatures. So here, let's look at an example. Again, we're looking at the temperature graph. So this is a very unique facility, actually. So they have, so these are the inlet fans. They have the inlet fans. So these are the supply fans pushing air in. And these are the exhaust fans. Okay, air moving perpendicular to stalls. So it is tunnel ventilated. Also, they have the cross ventilation fans, so air also moving parallel to animals. So, but these are also serving as supply fans. So, except these fans, all fans are pushing air in, and then exhaust fans are pulling air out. And as you can see, AMS units are here. So they have 4 AMS units, one here, 2 here, adjacent to each other, and one here. As you can see, this is the commitment pen area and the temperature. So pressure is coming from here. Temperature here is a little bit higher. So we can see that pale blue. So maybe from 28 to 29, so it increases. So since the increase is minor, it works for this barn. So it's not a like significant increase in temperature. But please remember, they have those big circulation fans, and they have a lot of, supplier fans, exhaust fans. They all help with the circulation and the ventilation. So, but I can see there might be some buildings. It is not the case for this barn. This is a beautiful barn. It works. But there might be some cases, depending on where the AMS units are placed, those areas might be problematic. There might be low airflow rate. So most of these barns are not brand new barns. They just purchased the AMS units and they have to put the AMS units wherever there is space. So it is understandable. But when there's a chance to choose if AMS units can be put by the, by the stalls, maybe this way or maybe this way, in this design there are feed alleys. There is not possible, but it can be. Then they will not block the air coming from outside, so they will not be an obstacle on the way. But this barn works, so this is a beautiful design. All right, so I started in Wisconsin about 2 years ago when I was hired. My campaign was the more ventilation is not always the better. And I still stick to my campaigns, so, and I will explain it to you. So Midwest Plant Service, so these are hot weather recommended ventilation rate for mature cows. What we understand from mature lactating cows are like around 1,400 pounds. So when we are doing ventilation design, the guidelines we use is the Midwest Plant Service 3234. So published in 1990. So recommended rate was around 469, 470 CFM per cow. So nowadays there's updated information, Dairyland Initiative from UW-Madison. At UW-Madison, they have a lot of good information available on their website. They have extensive studies related to ventilation design. And the updated number, they have publications in 2020, 21, 22, recommended rates are now as high as 1,500 CFM per cow. So double or maybe triple, we can think like that. So what are the reasons? So there are many reasons, right? Animals change, right? Things have changed. So maybe feed efficiency change, maybe production change. Yeah, they are still cows, but maybe they are not the same animals, right? Even the weight of the animals, they got bigger, right? Weight of the animals changed. And then also today we are talking about changing environment and climate. Maybe this climate change, maybe having these heat waves, they increase the recommended rates. Okay, so what happens if we keep increasing ventilation rates? So heat stress is a problem, right? It causes us a lot of economic loss. So what's going to happen if we increase that ventilation rates a little bit? So I think it will affect the electricity consumption in summer, right? So I'm kind of running out of time. Maybe Fred is saying something, but I cannot hear him very well. So let me summarize it very quickly, these last slides. So
Nelsa, you have plenty of time. You've got 15 minutes.
all right. So I want to save a couple of minutes for the questions. So let me go faster this part. So let's look at the recommended Midwest Plant Service recommended ventilation rates. It is 469 CFM per cow. Okay, so let's assume we have 700 cows. Let's assume our ventilation efficiency is 16 CFM per watt. And in summer, let's assume that these fans will be on when the outside temperature is above 20 degrees C. And there are 1,682 hours on average in Wisconsin that the temperature is that high. So this would be our electricity consumption, okay? And then if you look at the Dairyland Initiative, the updated, right, new recommended ventilation rates, so everything else is same. We still have 700 cows, 16 CFM per watt fan efficiency, and number of hours. The temperature is above 20 degrees C. So our electricity consumption will go up, right? So, okay, we can pay for that since we don't want to have heat stress. Heat stress has a lot of impact on economics, right? Economical impacts. So, but what happens to GHG emissions? So I'm talking about GHG emissions related to ventilation. So ventilation or energy consumption related GHG emissions. So here is the electricity consumption. So COMET is a tool. There are many different tools. I kind of find comment easy to use, so I always show an example using comment farm tool. Is approved, recommended by the NRCS, Natural Resources Conservation Service, in collaboration with Colorado State University. So let's look at the electricity consumption here. Okay, and then the tool calculates our total CO2 equivalents, GHG emissions, just ventilation related. We're not talking about anything else, just due to ventilation fans. And this is the updated ventilation rate, right? This is the new recommended ventilation rate. And this is our total CO2 equivalent GHG emissions. So the more we ventilate, the more we increase the ventilation rate, the more GHG emissions we have. We need to keep that one in mind. So the more GHG emissions we have, then it means that we will need a higher ventilation base in the future. So this is why I'm saying the more is not always the better in this situation. So it's endless, right? The more you increase, the more you need to increase. So one thing that we are shifting from ventilating dairy buildings to looking at that microclimate ventilation. I don't know what you would call it, maybe precision ventilation. So ventilating not the whole barn, but ventilating where the animals are, ventilation where we really need. So one project that we are working on, so this is a positive pressure tube ventilation in calf buildings. So you can see the positive pressure tubes here. So they bring fresh air from outside, and then they just provide air. They are projecting toward animals, providing air to the animals. So we are not air exchanging the whole barn air, but we are, projecting. So, and then we are working on a project to apply a different version of this positive pressure tube ventilation to dairy cows. These are small animals, but bigger animals, lactating cows. All right, so this is my summary. So I think rule number one is have adequate air inlets. So when these barns are designed, usually farmers think that they can open the garage doors and then air can come in. And it is always an option, but then there are birds, there are cats, they don't want those animals inside their building, so they just go ahead and shut down those garage doors. And there are buildings, they don't have enough air inlets. So air needs to come in to be able to come in. Otherwise, it increases static pressure, reduces fan efficiency. So we are aiming 40 to 60 air exchanges per hour in summer and 4 to 6 air exchanges in winter. And maybe in springtime, 20 air exchanges per hour. So having variable speed fans, ventilation fans, they help, right? Adjusting fan speed according to weather conditions. And then it's very important, I think it is the last thing you may want to do, but we need to maintain our fans, otherwise our fan efficiency goes down. There is data in the literature, they say if we don't maintain, efficiency will go by 40%. So energy consumption will be same. We will be paying the same bill, but less air will be moving towards the barn. And then if you're thinking about purchasing AMS units, placing them in a way that will not block the airflow rate is very important. So not maybe putting in front of the air inlet, and if there is a chance, there isn't always a chance, and it is understandable, but if there is a chance, putting them by the side wall, it will help so that air will not be blocked. So it will just come in from the air inlet and exhaust using the ventilation ducts. And this is my last slide. So with that, I want to open it up to questions. So this is my contact information. So if you remember my name, you will remember my email address. So it is nesli@wisc.edu. You can always email me. Otherwise, if you have any questions, I can try to answer now.
Thank you very much. Let's ask the folks attending to go ahead and type into the chat box if they've got questions. We've already got a couple. Kind of review with us the difference with the north-south versus east-west bonds, especially you'd indicated that there might be some shift in wind direction.
So the what I noticed, like when I looked at the data, it is not going to happen in near future. So it is still blowing from west to east. This is what I figured out. But there are some studies they are suggesting that it's gonna shift to north to south. So usually we want our ventilation fans to be on the east side so that there is no wind pressure on them. And then we want our ventilation air inlet on the west side so that the natural wind is contributing to our mechanical ventilation, right? So this is our design right now. But there are buildings they have that south north orientation. So in summer, since the when it's very hot, the wind blows from south actually. So when we really need ventilation, so in summer or during those very hot 1 or 2 days, if the air inlet is on the south side, then it does help too. So some farmers are saying to me, like, have your air inlet on the south side. So having that wind blowing from south when you really need that ventilation, so it will help. So I don't think there is a formula. Usually I think like west to east, like is easy, but there are barns north to south configuration orientation, so they also work well. So there isn't one formula that works for all. This is what I can say.
Yeah, maybe the other point about the east-west barns is that the summer sun tends to be up over top of it versus a north-south where you got that, especially in the afternoon, if there's a row of stalls on that west side, and there's a cement over there where that cement can get heated up and just all that heat actually gets into the barn. Definitely, yeah. So the east-west barns are definitely better. So another question, just the heat difference of like 3-row versus a 4-row versus a 6-row barn. And also like the more you kind of go to the 6-row, the more the wind tunnel tends to be more appropriate. But any comments on that?
For the cross or tunnel, are you asking?
Yeah, just when you take a look at the difference between 3 and 4 and 6-row barns, just the tendency would be the more you go towards the 6-row barns, especially that the more you're going to be looking at cross fence or I guess you could still do a wind tunnel vent, but yeah, just because natural ventilation, you just hold so much more heat in a 6-row barn.
Yeah, natural ventilation. It might be difficult. So natural ventilation, it works, if the ceiling is high and the barn is kind of small, so then you can exchange all that air. Yes, if there are many rows, maybe cross ventilation, but there's a limit for cross ventilation too, since the first rows inside the barn, they will be very lucky, right? But towards close to the ventilation fans, exhaust fans, is warming up. So if we have too many rows, then before reaching to exhaust fan, the air will warm up too much. Yeah.
Any other questions from anyone?
We've got a question that's coming. If we have an existing barn, is there, and we can't change the pitch, is there a way to mitigate a flatter pitch? I mean, is this something we can put in the barn or change to help get the summer heat out and still have it comfortable in the wintertime?
Yeah, this is what that farmer did, right? So they had the lower pitch. So let me go back. This one. So they had the lower pitch. So it was naturally ventilated barn and it didn't work. So what he did is he just put the ventilation fan. So it became from natural ventilated to it became to tunnel ventilated barn. So in summer, I don't think there is any other way. But since the ceiling is low, the amount of air they need to exchange is low. So putting these ventilation fans helps significantly. And then in winter, they can still go back to their original design, right? So this is the only thing that comes to my mind, I guess. Yeah, it was a very low barn, and as soon as I saw natural ventilation wouldn't work, like you don't need to make any measurements, you can see, and they have a lot of circulation fans too, more than maybe other regular barns. Yeah.
What do you see as the critical issue when retrofitting existing buildings?
So, if one issue that we start to see in Wisconsin is those AMS units, so where we put them. So, usually they are not brand new barns, so there is just a modified barn, right? They just put them, and depending on the flow pattern they usually choose that guided flow. Then ventilation, we need to pay attention to ventilation. Now, natural ventilation, if the AMS units are in the middle, it will not work. So now we need help. We need circulation fans. We need ventilation fans. So I think those, like, yes, we want those modern features, right? We want all those robots to be inside our building, but we need to think about how this air will move where we put these units. So I think it's the main concern right now.
We're going to go to maybe a more basic question here. When we have the fans midway in the barn, what's the right angle? Do you need to have a smoker to test them, or how do we determine how they're supposed to be set up to be the most efficient?
So the circulation fans or the ventilation? Circulation fans.
Circulation,
right?
Yeah.
Yeah, most of them I saw, they are kind of tilted, and we call it 45 degree. I don't know if it's the correct degree, but the ones that I observed in many, many buildings, they are 45 degrees, so towards the animals. So tilted. But it depends on the number of the circulation fans we have. So, but yeah, not vertical, always tilted.
Hey, we've got another question that came in. In your opinion, what is a better way to measure how many fans are needed? Is it the air change per hour, or the CFM per cow, or the theoretical airspeed in the beds?
Yes, so we use that, for example, it depends on the volume of the barn, right? So we know the volume of our barn, we know the ceiling height, right? We know the width, we know the length. So if we are aiming 60 air exchanges per hour, then we can calculate how much air we need to move. Then we know the fan efficiency. So maybe if you can give me their contact information, maybe I can send them the calculations. So if we know the fan efficiency, it depends on the model and the size of the fan. Then we can calculate how many fans we need to have that 60 air exchanges per hour. So to change the whole volume of the barn 60 times in 1 hour, how many fans we need to have. So yeah, one thing that we use is best lab, that's CFM per watt, like fan efficiency, since it's not like 100% efficiency, right? So it's the fan at the end, so it's to have an efficiency value. And then we need to know the volume of the barn. So usually length and the width, they're kind of like standard, but the height, it changes a lot. So some of them, they have a false ceiling, some of them, they have a higher ceiling. So depending on the volume of the barn. So if they can email me, I can show them the calculations, how we calculate how many fans we need to have.
Larry, are you seeing another question? I apologize, I didn't introduce Dr. Larry Trannell is my colleague from Northeast Iowa who's helping me with the questions today. Are you seeing anything, Larry? Okay. Final question. We have several listeners who are attending from very warm climates. Obviously, the very steep natural ventilation is probably the what we will see most in, for instance, Texas and Florida. What other recommendations are you seeing?
So we don't use much in Wisconsin, but sprinklers, right? Misters, soakers, they call it. So there are many different companies, so many different versions. So I don't know which one works the best, but it may help. So when, especially during that, heat wave time, right? If there is no wind blowing, it's very stagnant air, very hot. So having that sprinklers around may help. So it's the only thing that is coming to my mind other than, having mechanical ventilations.
Okay, I'm not seeing any additional questions in the chat. So at this point, I will thank you again for the presentation. Your contact information was on the last slide if folks have questions. And we will go ahead and put that into the archive within about a week or so. So again, thank you, and thank you
for having me. Yeah, thank you so much. Thank you.
And want to thank everybody who attended and remind them that we are going to next week on the 19th, we'll talk about mitigating heat stress for our employees. So we invite folks to attend that. Again, thank you. And
all right. Thank you for having me. All right. Bye-bye.